So I think we've established fairly confidently that OITS works for historical missions. Let's go on to future missions now. And let's in particular talk about, let's go back, an interstellar object. Now, what is an interstellar object? Well, this is an object that arrived in our solar system and came from outside of our solar system. So if you think of nearly all the celestial bodies that we know of in our solar system, they go around in ellipses. So they are bound to the sun, and they will continue to be bound to the sun indefinitely, in theory. That's not actually the case in certain circumstances, but they've been bound to the sun for a long period of time, and they will continue to do so. Whereas Oumuamua has a hyperbolic orbit, which is different from an elliptical orbit, so it came from an infinite distance or a very large distance, and it arrived with the speed of something like 26 kilometers per second with respect to the sun, and it will depart with the same speed. So the conservation of energy, of course, you leave with the same kinetic energy you arrived with. And we don't really know which star system it came from, or planetary system it originated in. We have some ideas, but not a very accurate idea. We do know it came from definitely outside our solar system, and definitely somewhere from within our galaxy, but we don't know precisely where. Let's try and get a mission to this object. So let's try and do this. These are the information. This is the information concerning Oumuamua. Is the name of the object, discovered in 2017, October the 19th. It's an interstellar object, first of all. As I say, it has a hyperbolic orbit, not an elliptical orbit. That means it came from a long way away. And it has the excess speed, the speed with respect to the sun, of 26.3 kilometers per second. So it's traveling at a fair lick when it arrived at the sun. It eventually reached perihelion, so it was accelerated by the sun, reached in excess of 80 kilometers per second, perihelion being the closest distance it got to the sun. And then when it traveled away from the sun, it slowed down again, slowed down by the sun's gravitational pull, and it'll be eventually departing the solar system in the direction of Pegasus. But it has a high inclination orbit. So that means that the plane of its orbit is quite highly inclined with respect to the ecliptic plane. And the ecliptic plane is that plane that Earth orbits the sun in. So it's got a hell of a inclination, this object. It was discovered after perihelion, which is a problem because that means it's a game of catch up. It's heading away from us. It's receding from the sun at a hell of a speed. So we need to try and catch up with this damn thing. And that's going to be a hell of a challenge. It has an unusual shape, and you saw that in the picture. That picture was just an artist's impression. We think it's more likely to be disc-shaped, in fact. So a flat pancake shape, one paper suggests is far more likely than a longitudinal shape, a high aspect ratio cigar. So that's strange. It had a perturbing non-gravitational acceleration. So there was a study into this object which determined its trajectory and worked out the influence of all the planets and the sun, the gravitational pull of all those objects on Oumuamua. And they found that there was an additional force not due to that gravitational influence that was at the time unexplained, and various theories have been proposed to explain this perturbing acceleration, this perturbing force, one of which was proposed by the prestigious scientist Avi Loeb, and he suggested that it could have been of artificial origin, this object. So it could be a solar sail. So what he was suggesting was that this perturbing force was due to radiation pressure, and so it was therefore very thin, just as a wind sail on Earth harnesses the power of the wind to propel a ship. So a solar sail in space harnesses the power of radiation, of light, if you like, from the sun, to propel a spaceship. So he's proposing basically it's a spaceship, this Avi Loeb chap. Whether that's the case, I'm not so sure. But the only way of finding out, if you think about it, is to send a mission. So we can look at it up close. And that's what I try to do with my software. Okay, so this is Oumuamua, and this is the plane of the ecliptic approximately. You see the planets orbiting. So you can see the scale of the challenge is traveling at high speed there with respect to Earth. So how are we going to catch up with this thing? So I studied this for a while, and I noticed that there was a study performed by an organization conducted by an organization called KISS, which is the Keck Institute for Space Science. and space studies rather. And it's conducted a workshop in 2014 studying missions to the interstellar medium. So at that stage, no interstellar objects have been discovered. So this was well before Oumuamua was discovered, for example. So they were studying missions into the interstellar medium, and that is well in excess of 100 astronomical units away. So it's a hell of a distance away. And what's more, we want to travel, they said they wanted to travel this distance to the interstellar medium in a very short time. So that means you need a high speed, if you think about it. To travel those distances, you need a high speed to get there so that it can reach those distances within 20 to 30 years. And this is precisely what we need to catch up with Oumuamua. We need a high heliocentric hyperbolic excess speed. In other words, we need the high speed with respect to the sun before we can catch it up, because it's traveling already with a high speed and it's heading away from us. So what solution did KISS come up with to get to the interstellar medium? So let's have a look into this. So what they did, let's ignore the first two bullet points for the moment and go on to the third bullet point. And the key issue here is that it travels to Jupiter. So the spacecraft is launched from Earth, eventually travels to Jupiter. And the purpose of traveling to Jupiter is so we can do a reverse gravitational assist. So instead of accelerating the spacecraft, it decelerates the spacecraft. So it puts on the brakes, the spacecraft. And then it does a free fall towards the sun to get a very low perihelion. So in other words, it gets very close to the sun, so a few solar radii from the sun, and then it puts on a spurt of rocket thrust. So it does a rocket burn. And this is known as solar burst. So at perihelion, that's, as I say, the closest point to the sun, it kind of applies a burn, a rocket thrust to propel itself. It's kind of slingshot maneuver to propel itself towards Oumuamua at a hell of a high speed. Except for the KISS study, it wasn't towards Oumuamua, it's towards the interstellar medium. But I thought, why can't we apply this logic to Oumuamua? Why can't we follow the same steps that KISS proposed to get to the interstellar medium to get to Oumuamua instead? So let's have a look at this. I noticed that there was a problem with the software at the time, that it didn't have intermediate points. There was no way I could have modeled something called the solar birth maneuver. And that's the thing that I touched on upon there. This is the solar birth burn. This is the thrust you apply at perihelion. So there's no way my software at the time could model a solar birth maneuver. So I came up with a notion of intermediate points. And this is what I'm going to try and explain to you now. What the user of the software does is he specifies a distance away from the sun. So this is the point, and R is the distance that the user specifies that this point is going to be away from the sun. And this lambda is the longitudinal, the longitude of that point. And phi is the latitude of the point, heliocentric longitude and heliocentric latitude. And those two parameters are then optimized by the optimizer, in addition to all the various other optimization parameters that it optimizes. So it kind of works out the best point of this location of the solar birth on a sphere, if you like. So with an intermediate point, we can, in fact, model a solar birth maneuver. So let's move on. So I've selected on the right-hand side here various celestial bodies. We're going to start off at Earth, naturally. We're going to get to Jupiter, naturally, because we want to lose all our tangential velocity to slow down in order to get very close to the sun. And then this intermediate point I selected, that was body number 3, and that is kind of going to model our solar birth maneuver. And then Oumuamua. So we arrive finally at Oumuamua. And having selected these 4 bodies, we can then select optimizer details. So this is where I open up my magnifying glass again. And we have on the top here, we have Earth data. And we look throughout 2003, the best launch date within 2003. And that was a result of lots and lots of study by myself. And I found 2033 was the best launch year to get to Oumuamua. And we've got various other data to get from, it's going to look within these time bounds that I specified. And this puts this 0.200279 That isn't the periapsis altitude, that is how close we're going to get to the sun. So this 0.0279 corresponds to this intermediate point. And this, in astronomical units, is how far we're going to get towards close to the sun, how close we're going to get to the sun in astronomical units. And it's about 6 or 7 solar radii from the center of the sun. So we're going to get very close. So this down space probe, is going to get very hot. So we're going to need a heat shield as well. And that's something that has to be factored into the equation. But we have various other data here. So let's now have a look at the solution that OITS comes up with, shall we? So let's do this. This is the solution it comes up with. And it turns out the optimal launch date is 2033, May the 8th, okay? And the arrival date to Oumuamua is 2052. So it's a 19-day hike, unfortunately, 19-year hike. So it's going to take a long time to get to Oumuamua. But it is possible. And you've got 18.2 kilometers per second delta V. That's the thing it was trying to minimize. And that means it can be launched, this probe, by a space launch system. And this is going to have its maiden flight, NASA's launch vehicle, which is going to have a maiden flight in the very near future, hopefully. Subject to delays over time, I should imagine. And 10.952 kilometers per second is required at Earth. Now, by doing a V-infinity leveraging maneuver, this reduces the overall delta V needed to get to Jupiter. So the delta V at Earth is reduced to 7.1 kilometers per second. So that means that the total delta V is reduced to 15.343 kilometers per second. So in other words, what I'm saying is, and this is lots of figures, lots of numbers, but what it comes down to is that we can launch a spacecraft towards Oumuamua. It would take 22 years, so the optimal launch date would actually be 2030, June the 9th. So it would take 22 years to get to Oumuamua, but it would be possible. And the question is whether we would want to do it. And there are various reasons why we might want to do it. For example, we might want to find out whether it is a spacecraft, whether it is of artificial origin. Another thing is, I think rather unlikely it is, but if it is, we'd like to know, because it's an opportunity not to be missed. Another thing is that this is of extrasolar origin. So in other words, it's made of matter material from another star system. And the only other way of actually getting to a star system, the nearest star system, would be using a rocket, using present-day technology, would be using a rocket, and that would be tens of thousands of years before we arrived at the nearest star system to our own, the Alpha Centauri. Proxima Centauri. So it's compared with those times, then to get to Oumuamua in 22 years seems to be much more doable in terms of achieving it in sort of a human lifetime. Let's have a look at the trajectory now. So let's have a look at the trajectory. So here we go. We launch from Earth. This is a V-infinity leveraging maneuver. So this maneuver allows us to get to Jupiter with less fuel expenditure, with less delta V. We then do a deep space maneuver at this point. Okay, and that slows the spacecraft, so it comes back towards the Earth. So it returns to Earth after 3 years. Eventually gets to Earth. Then we get a gravitational assist of Earth, and that propels it quickly towards Jupiter. So that whole business was just to reduce the delta V it takes to get to Jupiter, basically. Once you arrive at Jupiter, we get a reverse gravitational assist, and it slows down with respect to the Sun. And then it gradually accelerates, gets closer and closer and closer to the Sun. Of course, under the pull of the Sun's gravitational field. And then eventually gets to the Sun. At that point, we zoom out so we get a better view, and we can see Oumuamua coming into the field of view then. And it's heading away from the Sun. So that red dot is a spacecraft is now catching up with Oumuamua. This is all solved by the software. And eventually gets there 2052, I think you'll find. So there you go. That's my presentation. And she gets there.